with audio on. Yeah, so just kind of focus on what I say because I think it'll be fine. All right. So with question number one, I think question number one by itself has like 50 versions of it. So, but I do make sure that no one is getting a trivial case, like it's all zeros. Yeah. So my algorithm actually filters out things that are too simple to make it kind of more equitable, so no one can complain. Look at his version; it is so simple, and my version it has all the zeros and ones going all in all different directions. So they're all gonna at about the same difficulty level. Okay. So what I'll do is I'm just going to copy the whole thing, and so we have the bottom row being 1, 1, 0, 0. And I even label each row with its name, okay, which is important. So this is the row of all the carries. So we got 0, 0, 0, 1, 1, whoops, 1, 1, 0. These are the carries. And then the one on top is the Qs. And the Qs are unknown, which means you have to figure out the Qs as well. The y's are unknown, you have to figure out the y's, and the x's are unknown, you have to figure out the x's. Now there are certain cases where several things will work out. Okay, you just have to pick one. Okay, so let's check out this one. K0 being 0 is given. Okay, so that one we don't have to figure out why. Okay, but we know that whatever q is adding has to be a 0 because 0 plus 0 is a 0. But there's a carry here. So what can we deduce from here? Well, a few things, right? So we can at least deduce that this has to be a 0 because the sum bit being a 0 means q and k are both, well, k is already a 0, so q has to be a 0 because that has to do with the equation that we use to figure out the s bit. Then you go like, okay, 0 plus 0 is a 0, does not have a carry, but we do have a carry in the next column. Who can contribute to that carry? Well, you don't have a choice. It has to be coming from xy. So x has to be a 1 and y has to be a 1 in this position, in this case. Is that okay? All right, so next column. So for next column, what are the constraints? The constraint starts with a sum. The sum bit is a 0, but we already know k is a 1. So that means the q has to be a 1. Is that okay? Because otherwise I cannot end up with a 0 as the sum. Okay? But if q is a 1, that means one of these two has to be a 1 and the other one has to be a 0. It doesn't really matter which one because addition is commutative. So subtraction would be a little bit harder because subtraction is not commutative. But in this case, it is commutative. So you can put a 0 here and put a 1 here, or the other way around, it will still work. Doesn't really matter. Okay? And then we work on this one here. So it is given to you that the sum bit is a 1. The k bit is also a 1, which means the q bit has to be a 0. There's no choice, right? But then you look at the carry of the next column, it has a carry of 0. So that means in order to end up with a q of 0 here, we cannot have 1, 1 as xy. We have to have 0, 0 as xy. That's the constraint that limits what x and y can possibly be. So in this case, x has to be a 0, y has to be a 0. And here we are at the last column. So the last column has an overall sum bit of 1, but the carry is only a 0. So that means the q has to be a 1. Okay? If the q has to be a 1, that's easy for us to figure out the x and y. Once again, you can have this one being a 1, the other one being a 0, or the other way around, it will still work. So is that okay so far? Now, I know your numbers can be different, okay, because there are, like, as I said, I think there are 50 versions of this. But the reasoning is the same. I made sure, okay, that every single question has at least one carry coming from x and y in addition, and one carry that's coming from Q and K in that addition. So there's no escape from having to understand that part. Are we good with this one, number one? Okay. And you don't have to explain the reasoning. You just have to kind of fill in the numbers, because otherwise it would take a little bit too long to kind of put in your full answer. All right, let's go to question number 2. Question number 2 is to convert to base 10 step by step, and this is a base 4 number. All right, so if it's a base 4 number, what do you do? The first thing I would do is really just to have a little table of what each digit is representing, but I can always do it like this. Okay, so I will say 2001.2 in base 4. I cannot do subscript using a plain text editor, so I'll just break it down as 200. What? That we would be relying on keyboards. They would not have used all this fancy notation. That's a good observation. They obviously do not care. Okay, so I would just break it up like this. Are there any questions about this step? I think I used exactly the same steps in class 2. So I just break out, it's 200. Don't call it 200 because 200 implies is a base 10 quantity. This is just 200 in base 2, base 4, excuse me, 00 in base 4. If you don't write this one out, it's fine. Okay, I'm not going to take any points off. There's a 1 in base 4, and then there's a 0.2 in base 4. Okay, so what does that mean? Well, that means we have a 1 times 100 in base 4, and I'm going to skip the 0 because it's just not going to do anything useful, and 1 times 1 in base 4, and then we have a 2 times 0.1 in base 4. And then we look at this and go like, well, what exactly is 100 in base, whoops. I made the mistake copying from one row to the next. It's 2, okay, 2 of the 100s. 100 in base 4 is 4 to the power of 2. The number of zeros after the 1 tells you to what power are we raising the base, okay, when it's to the left-hand side of the decimal point. So now this one is 4 to the power of 2. And then this is 1 times 1 to the power of 0 because there are no zeros to the right of that 1. And then we have 2 of these things. Now this one is really just okay, that's 4. So the other one is 4 to the power of -1. Okay, because when we move to the right hand side, the powers just keep decreasing. If it's to the right hand side of 4 to the power of 0, becomes 4 to the power of -1, and then -2, and so on if I have more digits to the right hand side. Is that okay? So left hand side is increasing power, right hand side is decreasing power. Okay, so once I get to this point, I do not have base 4 numbers anymore because everything now is base 10. So 4 to the power of 2 is 16, and we have 2 of those. So 2 times 16 here, plus 1 times 4 to the power of 0, which is just 1. And then we have a 4 to the power of -1, which is 1 divided by 4, which is 0.25. But 2 times okay, we'll spell it out. Okay, there we go. Okay, so now it is just a matter of adding up the values. This is 32 plus 1, and that's 0.5. So one last row will finish the entire calculation. It is representing 33.5 in this case. Do we have any questions about number 2? Now, obviously, your digits will be maybe different, or more likely than not, they're a little bit different. But they should not be different to the point where it is significantly more difficult or significantly less difficult than this. Because in the random generator thing that I did, I kind of made sure that it is about the same kind of difficulty. Do we have any questions about this one? This is good so far? Okay. So let's move on to the question number 3. So question number 3 is kind of the reverse. We are now converting a base 10 number or a value expressed in base 10 to a number that is going to be expressed in base 5. So it's exactly the opposite. I pair up these questions because if you remember how to do one, most likely it would trigger your memory of how to do the other one. So if you remember just one of them, the other one is kind of like, oh, it's exactly the opposite, okay? Which is in this case is the exact opposite. So we'll write down 34.48. So this time it is 34.48 because it is a decimal number. And now we have to express it in quantities of powers of 5. Okay, so before we do anything, I think it may not be a bad idea to spell out some powers of 5, right? So we'll start with 5. 5 to the power of 2 is 25. 5 to the power of 1 is 5. Okay. 5 to the power of 0 is 1. Okay. 5 to the power of negative 1 is what do we know it as in base 10?
1 over 5, which is 0.2.
0.2. Very good. And we might need the other one too. 5 to the power of negative 2, which is 1 divided by 25 is
0.04.
0.04. Thank you. Very good. And to get to this table, you don't really need a calculator, but if you have a calculator, that can kind of boost your confidence in these numbers. But otherwise, you don't really need that. I mean, 1 divided by 25, you just look at it as 1.00 divided by 25, and you get 0.04. So that's not it's definitely doable. So we look at all of these things and go like, it's really the same thing as this is the amount I want to give to someone. But what do I have as bills and coins? I got $1 bills, $5 bills, $25 bills. I got 20 cents, and I got 4 cents as my coins. So how do I make up $34.48? That really is the question. If you know how to work with quarters, dimes, nickels, which have no regularity whatsoever, this is actually easier. It should be easier, okay? So you look at this number and go like, okay, we can easily pick out the 25, right? So after the 25, we got 9 left here. So of the 9, it's a 5 plus a 4, okay? And then we have the 0.48. So you look at the 0.48 and go like, okay, so if I have 48 cents of change, but I only have 20 cents coins and 4 cent coins, how do I make up 48 cents with the least number of coins? I'm going to maximize the use of the 20 cents coins first, right? So 48 cents is going to have 2 of those. Okay, so we'll say there are 2 of those. Okay, I'll use the multiplier on the next row. Okay, and then we'll be left with 0.08. So that's my first row, and then I start to use quantifiers. Okay, oops, the other way around. 5 to the power of 2 plus 1 times 5 to the power of 1 plus 4 times 5 to the power of 0 plus 2 times 5 to the power of negative 1, because 0.2 is 5 to the power of negative 1, and we need 2 of those. And then we also need 2 times 5 to the power of negative 2. Okay? So now at this point, you just say, oh, okay, so it's 1 times 100 in base 5. How do I know, 5 to the power of 2 is 100 in base 5? Exactly. The power that you raise it to is the number of zeros that you need. Okay? And so we can work with the other ones, which is 1 times 10 in base 5 plus 4 times 1 in base 5 plus 2 times 0.1 in base 5. Okay, I'm going to move this one a little bit here. Plus 2 times 0.01 in base 5. Okay, can I answer any questions back there? Yo. Y'all. Okay, they're quite absorbed in their conversation. Hello. Can I answer your questions? Okay. But we are trying to, kind of, if I can hear you, so can the rest of the class. So, thank you. Yep, okay. All right, so here becomes just 100. This is just 10. That becomes 4. That becomes point 0.2 in base 5, and then that becomes 0.02 in base 5. So all of these are still are definitely in base 5 now. So we'll make it extra clear that we are dealing with base 5. Now, if you forget to put all the base 5 suffixes, in these steps, as long as it is clear how you got to these numbers, I'll probably just let it slide. So now you just add up all of these things. It becomes 114.22 in base 5.
So
Yep.
if I skip like line 9 or line number 23, would I lose points?
You mean you went from here directly to
Yeah.
here? You'll be fine.
Okay.
Yep. Yep.
So in the very beginning of this problem, you took 34.48, and I guess you recognize that that's 4 digits, and so
Mm-hmm.
you're only going to 5 to the power of 2, and then 5
Yeah.
to the power of negative 2.
Yeah.
That's how you know
Yep.
you only go that far.
Yep.
Based on there's only 4 digits, I should only.
Right. So if I did not use a 25, then I will say, oh, there are 6, right? There are 6 fives. And then 6 is more than 4, which is the largest digit you can use in base 5. So I know I need another power of 5 in that case. Yep. So is that okay so far in number 3? Okay. So that's number 3, and then moving on to number 4. So number 4 is it's both a trick question but also a very easy question. It's a trick question if people keep thinking in the mindset of, oh, we saw a question like this in the practice test, and the answer is regardless of the number of bits, it's the same. Okay, so those people would be tricked by me because they did not look into what I'm really asking. Okay, but this question is not asking about the amount of time or the level of gates. This one is asking about how many inputs are we feeding into the final OR gate. Okay, so you can look up your own designs. Okay, you can look up the design for your K3, K2, and K1 in your homework assignment. You go like, okay, here's K3, and how many things are feeding into that final OR? 4 things. What about K2? 3 things. So you have a pretty good idea that, okay, maybe if we're concerned about K20, there should be 21 things feeding into it, right? But how do you convince me that that is the case? Okay, just because you have some observations based on K3, K2, and K1 doesn't mean it holds true in general for any K. So what do?
Start a module on.
You go to my module, exactly. And it is open book, open notes. Okay, so you can definitely just completely copy and paste it, even cut and paste. Okay, use a pair of scissors, cut it out, get some scotch tape, put it there. I don't see why not. I mean, So that would be in adding binary addition. So you go to binary addition, and then it goes to section 6, and then you go straight to the end of section 6 and just go like, okay, where are the ORs? Here's a gigantic OR, and here's another OR. Yep, so you just count, okay, how many times do we have to do it? Yep. Mm-hmm.
I thought that equation was meant to calculate the number of levels and the max, like the numbers.
Which equation? This one?
Calculate the levels of gates.
It will tell you the level of gates as well. There are 3 levels. But when you look at the gigantic OR, which is combining all of these ORs and this last one, that tells you how many inputs are going into that one final OR gate.
Okay.
Now the tricky part is, but this is going from 0 to n, so that means there are n plus 1 inputs to that OR. But you have to remember, you have to subtract 1 from this suffix to get to here. So if I'm asking about, what was it again? Okay, let's say it's K24, okay? If I'm asking about K24, n is 23. So from 0 to 23, you have 24 inputs plus this extra one. So that makes 25 inputs to the final OR gate. So that would be the explanation, okay? Maybe not in those exact words, but you got to quote this and go like, okay, there are this many ORs coming from here, and then one more from here. Done. Okay? All right. So let's move on to the next question, number 5. Okay, number 5 is interesting. Okay, I did not anticipate a whole lot of questions regarding question number 5, but I got some, which is fine. Okay, so let's look at the number here. It's 1110 and then 1100. Okay, so I'm just going to copy the number here. So it's 1100 in base 2. And I want to look at this as a signed number, a signed integer, and I want to know what value it is representing. I can see two major ways of doing this, and you can choose which way, both ways are equally acceptable. There may be some additional ways that I'm not aware of, but as long as you can explain it step by step, logically, and I see the logic is sound, I can still accept that as an answer. Okay? But I can tell you right away which two are the ones that I look for. Okay? So the signed interpretation, okay, so I'm going to use value to indicate the value represented by that thing, 101100 in base 2. In this case is basically 01100 in base 2 minus the 100 1 2 3. There you go. Okay, that's the value represented by that bit pattern. You add up the powers of 2 except for the most significant bit, that gives you 1 sigma, and then you subtract, if the most significant bit is a 1, you subtract that amount from the other sigma. Okay? So in this particular case, okay, we'll look at this part here. We got 1, 0, 1, 0, 2, 1, 4, and 1, 8. So it's 4 plus 8 here, minus, huh?
Answer in binary, would that be okay?
How can you give me an answer in binary? If the question is already presenting a binary number and asking for the value represented.
I thought I was trying to go from a 2's complement to the actual.
You can, okay, so wait, just wait a little bit. I will deal with the 2's complement. So now I can now look at the second one. 1, 2, 4, 8, 16. This is 32. So I subtract 32 from the other number, which ends up to be 12 minus 32, and that is negative 20. Okay, so that's one way. Second way. So the second way is to say the value represented by this particular bit pattern is less than 0 because the sign bit is a 1. Now you have to use this first to explain why you're applying 2's complement to it. Because if you don't explain this first, why are you applying 2's complement? What is the purpose of 2's complement? 2's complement is flipping the sign, right? So you only want to flip the sign if you know the value is negative to begin with, and you're just trying to figure out how negative it goes. So you have to explain it and say, oh, the sign bit is 1, that's why we're applying 2's complement. Okay, so once you know that, then you can say, oh, okay, so that means the value is the negation of C2 2's complement of 101100 in base 2. Because technically speaking, 2's complement is negation. So we have double negation, so the value is not changed. And that's why I can still use an equality here. Is that okay? All right, so knowing that, I keep the arithmetic negation on the outside, and I now try to figure out the 2's complement, which is 1's complement, 101100 in base 2, plus 1. And then I keep the negation on the outside, the arithmetic negation. Now it becomes 010011 in base 2 plus 1. And now it becomes the negation of 0101 100 in this case in base 2. So if this is what you meant when you said you're giving me the answer in binary, I can give you most of the points because the answer should be in base 10.
That's what I did.
That's what you did?
Yeah, I put my answer because I used x minus x equals 2 to the 6th and then I did some arithmetic and I just put a negative in front of the answer after I found x.
But where's that negative coming from? You have to explain why you have that negative. Yeah. And in here, I explained that by saying, because the sign bit is a 1, so I know the value represented is negative to begin with. So, but since C2 is also a negation, so minus C2 is double negation, it cancels out, and that's why I can use this derivation to get to negative 20. But I would say the other one is a lot simpler. It's just straightforward. And it's directly from the modules, too. Yep.
You had to know that there's a negation in front of C2 in order to...
Right, because I want to know what is the value represented, right? So the value represented is not 20. It is negative 20. So, but I do know that, arithmetic negation and C2 are really the same thing. So when you use arithmetic negation and C2 in conjunction with each other, they cancel out. So in return, in effect, I'm still looking at the value of this thing here. Okay? So I'll look at how you guys phrase it, because it really just depends on how you phrase it. Okay, question number 6. Okay, question number 6. Let me see if I can copy and paste the numbers. Okay. Now this one looks nasty, but if you remember what a floating point number is and how the bits are allocated, shouldn't be that difficult. Okay, so the first step is to break it down back into binary digits. Okay. If you forget the table, the hexadecimal to binary table, you can just make it up on the fly during the exam. Because all of those entries is just adding 1, adding 1, adding 1, adding 1, adding 1. And on the digit side, you have 0 to 9 and then A, B, C, D, E, F. So it should be doable during the exam, even though it might burn like 2 minutes of your time to do it. Okay. So here we have a 4, which is 0, 1, 0, 0. And then a 0, which is 0, 0, 0, 0. A 6, which is 0, 1, 1, 0. And A, which is 1, 0, 1, 0. And then with the rest are all zeros. Okay, so I'm not too concerned about the rest. So now we have to identify what those things are. This is my sign bit. These are all E's. There are 11 of those. And then these are all fractional part of the Mantissa. So I'm going to use these letters to indicate what those things are. So now we know the sign is a 0. We know E as a binary number. Hold on a second. 1, 0, 0, 0, 0, 0, 0, 0, 1, 1, 0. Yes?
I apologize. I'm sorry. I got it.
Oh, okay. And then we also know the Mantissa. Okay, so the Mantissa is 1 point and then the fractional part. So in this case, we have 1.1010 in base 2. I mean, the rest are all 0, so there's no need to write them. Are we doing okay so far with this? Yes?
1.01?
It's okay, so 100 and then all zeros, that's the fractional part of the Mantissa. The 1 point is implied.
Oh, okay.
It's always there. We do not represent the 1 point. Okay? So that's why this is the Mantissa itself. But the actual exponent, okay, so the value represented is 1.1010 in base 2 times 2 to the power of, now this part you have to be careful because it's not one, let's see, we have 7 zeros, 1, 2, 3, 4, 5, 6, 7, 1, 1, 0 in base 2. That is not, because it's biased. You have to remember to subtract 1023 from that value to be the actual exponent of 2. So we look at this and go like, well, can we rewrite this a little bit better? It's 1 plus 1/2, no quarters, but we do have 1/8, okay? times 2 to the power of, that is the same thing as 1024 plus 4 plus 2, which is 1030. Okay, 1030 minus 1023 is 7. So we end up with just 2 to the power of 7. So we end up with 1.625 times 128. If you run out of time and this is what you give me, I'll take it as a complete answer. In case you forgot to bring your scientific calculator or any calculator, and you don't want to do this calculation by hand, I'll take it. Yep.
If I gave you the decimal representation, just the whole string, would that be fine? Not using the Mantissa or literally wrote out every digit.
Well,
Big long number to look at.
it depends on whether that long number
It's the right
is the actual value represented by the double. Because otherwise I can just write a really long, base 10 number, and that doesn't necessarily get you any points. Now, in this case, if you do want to do the bit shifting, there are other ways to figure out the values too, because you can always do the bit shifting, because it's 2 to the power of 7, right? So you can just imagine this point going like 1, 2, 3, 4, and then 5, 6, 7 over here. Then you can actually figure out the value as well. There are many ways to get to the answer. You can do the bit shifting or the point shifting before we do the conversion back into base 10, or you can do it after we convert it back to base 10. So there are quite a few ways to do it. So the bottom line is the quantity is going to be about a little less than 200-ish. Shouldn't be very long. Yeah, that probably is not it.
I'm just confused. So why can't I just say like this is like
Oops.
4, 8, and 12. Why can't I say that this is like 16 to the 8th place?
16th to the 8th place.
If I'm trying to look like, so that's
Because it depends on what those bits are for. Because those bits are the fractional part of the base 2 Mantissa. That's what they're for.
okay.
Yep. So you have to know how to interpret the bits inside the 64 bits.
Okay.
Yep. And there are multiple ways to get to that part. The Wikipedia page has 2 equations to do it, and I think in my notes I also mentioned how to do it. So there are equations to do that. All right. Next question. The next question is the exact reverse. So question number 7, in my case, in this case is starting with a value of 60, and I want to go back to the double representation. So what do? Exactly the opposite of what I just did. Okay, so you look at 60, and you ask, this is 60 in base 10. How do I express this as 1 point blah, 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 blah in base 2 times 2 to the power of something? Okay, I need to get it into that form. How do I get it into that form? What about we just look at 60 as a binary number first? Okay, I think that might be a good first step to take. Okay, so we now say, okay, 60 is, if you want to go really step by step, you can say it is 32 plus 16. That makes up what? 48. And we got 12 left, which means we have an 8 and a 4. Okay, so that becomes 1 followed by 5 zeros, 1, 2, 3, 4, 5 in base 2, plus 1 followed by 4 zeros, 1, 2, 3, 4, plus 1 followed by 3 zeros in base 2, plus 1 followed by 2 zeros in base 2. Then I add up these numbers and go like, okay, that becomes 1, 1, 1, 1, 0, 0 in base 2. So at this point, I'm going to look at this and go like, that seems pretty unlikely, okay, having 4 consecutive 1s and 2 zeros. Okay, it doesn't really make sense. So I look at 60 as, oh, it's 63 minus 3, okay, right? 60 is 63 minus 3. 63 is 64 minus 1, which is 2 to the power of 6 minus 1, which means it is 6 ones. Okay, 63 itself is 111 in base 2. 3 is 11 in base 2. So you have 111 minus 11 in base 2. Yeah, that seems to make sense. So I would go through all that stuff in my head just to make sure that I didn't make some stupid mistake because it, really? 4 consecutive ones? Yep, really. Okay. So then what do we do? Because we really want to look at it as something like this, okay? And right now it's not. So if you want to be totally step by step, then we can just say, let's put a binary point there. Okay, the binary point doesn't do a single thing because we don't have any fractions yet. But then we can say, oh, we can shift that binary point by adjusting the 2 power of 2. Who's that? What are they doing?
Hi,
Hello.
sorry to interrupt, but somebody thinks they might have left a mouse in here, like
A mouse.
a Logitech wireless mouse.
Okay, do you guys see any? We really need a cat for a mouse hunt. Oh, right. Okay, somebody pick this up.
Oh, is it Logitech?
Well, but does it belong to the classroom?
Oh, I have no idea.
Yeah, because the classroom has its own cordless mouse too. Okay, let me see. Nope, it's not the classroom's.
Oh, okay, nice.
Yep,
Thank you.
sure.
Oh, perfect.
Okay. All right. So getting back to here. Does that make sense? We're shifting the binary point that way. Every time we shift the binary point, we're dividing the mantissa by 2. So we have to make up for that division by 2 by multiplying 2. But multiplication by 2 is just increasing the power of 2 by 1, which was implicitly 0 from before. So it went from 0 to 1. And you can probably just count how many times we have to do this. So we have to move this point how many more times? 1, 2, 3, 4. 4 times. So we can just say 1, 1, 1, 0, 0 in base 2. And then we also have to remember to raise the power of 2. 4 more, which is 5 in this case. Okay? All right, so what is this buying me? Well, first of all, I know the sign is 0 because the quantity is non-negative. We know E is the bias, which is 1023, plus the actual value that we want, which is 5. And we also know the fractional part is 111,000, all zeros after that. That's what we know. But wait, E is not a binary number. Well, let's convert it into a binary number then. So that becomes 1028, which is 1024 plus 4, which is 1 followed by 10 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, plus 100 in base 2. Okay, so I got to make sure that it is clear where I switched to binary. So now the E is, okay, I'm just going to be a little bit lazy and copy and paste. Copy, paste, and then just change one of the digits to a 1. Okay, and now we can reformat the whole thing. So the 64-bit for the double is a 0 for the sign, and then we have the E, which is 1 followed by how many zeros?
8 zeros and then a 1.
Not 8 zeros, 7 zeros. Yep. So it's 1 and then 1, 2, 3, 4, 5, 6, 7, 1, 0, 0. And then we have the fractional mantissa, which is 1, 1, 1, and then all zeros after that. And then we group these things into groups of 4. So the first group of 4 is just 4 itself, because 0, 1, 0, 0 is 4. The next group, which is 0, 0, 0, 0, is another 0. The next group of 4 is 0, 1, 0, 0, which is another 4. And then we have 1, 1, 1, 0, which is a C.
Yeah. 13?
Yeah, no, that's 14.
I'm sorry.
It's an E. It's actually an E.
Oh, it's an E.
1110 is 2 plus 4 plus 8, so that's 14, which is an E.
Sorry.
And then the rest are all zeros. So if you get to this point, I'm gonna give you like most of the points. Because you still need to kind of let me know how many zeros there are. Now, unless you say dot 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 means how many zeros, but I would much rather have you to spell out the entire thing. So that becomes 0x 404E0. That accounts for 5 of the 16 zeros. So we need 11 more. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. There we go. So you can see how this is really kind of the reverse process of the previous question. If you nail one, it will tell you kind of how to approach the other one. And that's the whole test.
So there should be 16 bits.
There should be 16 hexadecimal digits.
Hexadecimal digits, yeah.
Right. But only the first 4 are really significant. The rest are all zeros. So if you figure out the most significant 4 hexadecimal digits correctly, and you just go like dot 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 for the rest, I'll give you like most of the points. Yep. Do we have any questions about the 7 questions?
Um,
Yep.
can you explain again why it's an applied one? It has the Mantissa part. Like 60 equals.
That's part of the rule itself. That's part of the specification. So the specification says, the bit 0 to bit 51, those are the fractional bits. Yep.
Yeah.
All right. So I'm going to grade these things, based on, what you write down. Mostly, it's the reasoning. So if you write down the reasoning, everything is sound, and it seems like you follow the steps, and then somewhere you go like, okay, I just copy the 0 into a 1, and so the final answer is kind of incorrect. I'll give you most of the points because it's just a stupid mistake, not because you did not understand the concept. On the other hand, if somebody just write down the final answer, it's not going to worth a whole lot of points because I have no idea what went through, what process that person went through to get to the answer. So this will take me some time to grade because this class has 32, 33 students. My 440 class has 50 students. And then my other assembly class has, I think, 22 or 21 students. And each one is kind of like this, all open-ended questions. And for those of you who know me, I destaple every single exam, run it through a scanner, so I have a digitized version of all of the questions, and then I grade it based on the PDF documents. And then for each question, there'll be multiple rubric items, and then for each item, I would go through the rubric and go like, okay, where does this answer fall onto? Does it demonstrate blah blah blah, or does it show understanding of blah blah blah? So I have to look at that scale and go like, it's about here, and so on. So this will take a long time because you guys are talking about 100 students or 100 exams times 7 questions to each exam, so 700 questions. Each question usually breaks down to 3 or 4 individual items, so that's like 28 rows of rubric items that I have to go through.
What
Yep.
about if somebody uses an alternate technique and that doesn't quite fit into your rubric?
Um,
Because I noticed that sometimes, like when on a test I did induction, but I did mathematical induction in more of a free form way
mm-hmm.
instead of going like step by step. So if that doesn't fit in your rubric, what do you do? Like say you have we're converting a number to base 2,
Mm-hmm.
and we use an alternate method that doesn't include like the counting money method,
It has to be a systematic method that I can see.
Okay. Okay.
It cannot be, I feel this is the binary representation. That wouldn't work.
Okay.
Yeah, so it has to be a systematic method that I can see and I go like, yep, I know that method too. That method is sound and it works. So it doesn't have to be a method that I have talked about, but it has to be a very systematic way that is actually correct. Yeah. All right. Any other questions? No other questions? We're good? All right. So I'm going to stop the recorder or the streaming. That's the only stream that I have done in 2